Dear students, today we are discussing 5th semester course subject linear algebra. Chapter name is Quotient Space, Contents, Objectives, Introduction, Quotient Space, Quotient Subspace and worked out exercise. Check your progress, model answers, model examination questions. Objectives: determine the concept of a coset of a subspace of vector space and the quotient space of a vector space by a subspace and quote certain examples of these. Prove certain important elementary properties of quotient spaces and determine the dimensions of a quotient space. Introduction: when W is a subspace of vector space V over F, then W is the subgroup of group V comma plus, and hence we have the usual concept of coset and quotient group V by W together with a natural scalar multiplication actually becomes as a vector space over the same field F. In this unit, we shall prove certain important properties V by W of V by W, coset of a subspace. We have observed earlier that any straight line passing through the origin in the Euclidean plane, if L is any straight line in R square, then L can be expressed as x plus W for a suitable x in R square and a subspace W of R square. Such set is called a coset of W. Definition: that is normal definition, this is mathematical definition. Let W be a subspace of vector space V over F, F means field, for any x belongs to V, V is a vector space. Let us define x plus W equal to, within the set symbol x comma y, such that y belongs to W. Here x plus W is called a coset of W corresponding to x. Check your progress. Let V be any vector space over and field F and W be the subspaces of V, then prove the following. Theorem: first one, most important theorem. For any x comma y belongs to W, x comma y belongs to V, x plus W equal to, then prove that x plus W equal to y plus W if and only if x minus y belongs to W. Proof: let x comma y belongs to F. If x plus W equal to y plus W, then x equal to x plus 0 belongs to x plus W, that equal to y plus W, and hence x equal to y plus z for some z belongs to W, and hence x minus y equal to z belongs to W. Conversely, suppose that x minus y equal to z belongs to W. Conversely, suppose that x minus y belongs to W, then x plus W equal to y plus x minus y plus x minus y plus W is subset or equal to y plus W, and hence x plus W equal to y plus W, hence proved. Next theorem: any two cosets x plus W and y plus W and either disjoint or equal, either x plus W intersection y plus W equal to null set. What is null set? There is no elements in it, or x plus W equal to y plus W. Proof: suppose x plus W intersection y plus W equal to null set, choose z belongs to x plus W intersection y plus w, then z equal to x plus s and z equal to y plus t for some or for all for some s comma t belongs to w, and hence y plus s equal to y plus t. So, that x minus y equal to t minus s, which is belongs to w. Thus, x plus w equal to y plus w by previous theorem. This completes the proof of theorem. Example part 1. Let set of all points on a straight line L, then passing through the origin in R square, then W is a subspace of R square. Any coset of W is straight line parallel to L, and conversely any straight line parallel to L is a coset of W, is a straight line parallel to L, and conversely any straight line parallel to L is a coset of W. To see this, y equal to mx, where we listen this y equal to mx plus c in coordinate geometry, equation of a straight line passing through equation of a straight line in slope intercept form. Here slope equal to m, x intercept is c, here x intercept is 0. So, be the equation of a given straight line w equal to a comma b belongs to r dash, such that b equal to m a. Let x equal to s comma t belongs to r square, then the coset x plus w is given by x plus w equal to within the set symbol x comma y, such that y belongs to w by definition, that equal to s comma t plus a comma b, such that b equal to m a, that equal to s plus a comma t plus b, such that a comma b belongs to r and b equal to m a. Part 2. You can easily see that c comma d belongs to x plus w if and only if d equal to m c plus k, where k equal to 1 minus m x. Thus, x plus w is straight line whose equation is y equal to m x plus c. This is also a equation of a straight line in slope intercept form. Here slope equal to m and x intercept is k, and therefore is a straight line parallel to L and passing through the point s comma t. Conversely, suppose L is a straight line parallel to L is of the form y equal to m x plus k, where k is constant if y equal to u comma theta is an arbitrary point of L dash, then theta equal to mu plus k, and hence k equal to theta minus mu. So, that the equation of L becomes y equal to m x minus u plus theta. You can easily verify that a comma b belongs to R2, a comma b belongs to L dash if and only if b minus theta equal to m into within the bracket a minus u if and only if a comma b equal to u comma theta plus a minus u comma m into a minus u. If and only if a comma b belongs to y plus w, and therefore L dash equal to y plus w, that means L dash is coset of w. Quotient space. The quotient of subspace W of a vector space V over field F form a new vector space over the same field F. We shall prove this in the following theorem, most important theorem. let W be a subspace of vector space V over field F. Let V by W be the set of all cosets of W in V. That is, V by W equal to within the sets X plus W such that X belongs to V for any X plus W, comma Y plus W belongs to V by W. Define X plus W plus Y plus W equal to X plus Y plus W. Here observe, student, here W plus W, that is 2W, 2W is equal to W, because in integration we will do constant C1, C2, C3, all are equal to C only, right. Like that same way, here you should not write 2W, here W, 2W is equal to W. That is why variables X plus Y plus W we need to write. Yes. Next, addition, product, A into X plus W equal to AX plus AW. AW is nothing but W only. For all A belongs to F, F is a field. Then with these equations, V by W is a V by W is a vector space over F. First, we have to prove that the operations on addition plus on V by W and the scalar multiplication in V by W are well defined in the sense that these depend on the cosets X plus W, but not on the element X. Recall that X comma X dash belongs to W, X comma X plus W equal to X dash plus W, if and only if X minus X dash belongs to W. Now suppose X plus W equal to X dash plus W and Y plus W equal to Y dash plus W. For all Y comma Y dash belongs to W, then X minus X dash and Y minus Y dash belongs to W, and hence X plus Y minus of X dash plus Y dash equal to shuffling. Shuffling means adjustment. This can be written as X minus X dash plus Y minus Y dash, which is belongs to W. So that X plus Y plus W equal to X dash plus Y dash plus W. This shows that plus addition is a well defined on V by W. What is V by W? Is a quotient space. Also, for any A belongs to F, F is a field. So, AX minus AX dash, this can be written as, take A is common, A of X minus X dash, which is belongs to W. So, that AX plus W equal to AX dash plus W. This shows that scalar multiplication is also well defined. Part 2, proof. To begin with, V by W plus is clearly is an abelian group. Abelian group means, abelian group is also known as commutative group. If any group satisfies abelian commutative property, then we will say that is abelian group. What is commutative property? A into B equal to B into A. So, since W is subgroup of abelian group, V comma plus, recall that 0 plus W equal to W, 0 plus W equal to W is the identity element, and minus X plus W is the inverse of X plus W is the identity element, and minus X plus W is the inverse of X plus W in V by W comma plus, means quotient group, that meaning. For any X plus W comma Y plus W belongs to V by W and A comma B belongs to F, we have A into X plus W plus Y plus W, that equal to A, we took outside common, X plus Y plus W, that equal to A into X plus Y plus W, that equal to A x plus ay plus w, that equal to adjustment, means ax plus w plus ay plus w. This can be written as a into x plus w plus a into y plus w, and similarly we have a plus b x plus w. This can be adjustment a into x plus w, a into x plus w plus b into x plus w. Next one, a b into x plus w, a b into x plus w, that equal to a b into x plus w, that can be written as a outside within the bracket bx plus w, that can be written as a outside bx plus w, that can be written as a outside, b is also outside, x plus w. So, finally, 1 into x plus w can be written as 1 into x plus 1 into w is nothing but w, that equal to x plus w, where 1 is the multiplicative identity in F, means field in F. Then all the axioms satisfied, and hence V by W means quotient space is a vector space over a field F, over a field F. This completes the proof of theorem. Definition: the vector space V by W constructed above is called the quotient space of V by W, or simply the quotient space V by W. Theorem: most important this is also, that W be subspace of a finitely generated vector space V over a field F. Then W and V by W are both finitely generated, and dimension F V equal to dimension F W plus dimension F V by W. Proof part 1. Let dimension V equal to n and B equal to x1 comma x2 comma etc. xn be a basis for V over a field F. Then L of B equal to V, and B is linearly independent over F. Also, any linear independent set in V has at most n elements. If W equal to 0 and V by W equal to V and W equal to 0, so that the theorem becomes trivial. Now, suppose W is not equal to 0, then choose 0 is not equal to 1, that belongs to W, such that y2 does not belongs to L of y, L of y1. We get that y1 comma y2 linearly independent over F. If W equal to L of y1 comma y2, then y1 comma y2 is basis for W, basis for W, and W equal to 2. If W is not equal to L of y1 comma y2, and continue this process with the linear independent set y1 comma y2, then choose y3 is not equal to L2 y1 comma y2. Proof 2. This process cannot be continued indefinitely, should be terminate say at nth stage by yielding linearly independent set y1 comma y2 comma so on ym in W over F, such that W equal to y1 comma y2 comma y3, that is y1 comma y2 comma etc. ym is basis for W, and hence W equal to m, since y1 comma y2 comma etc. ym is linearly independent in W. It is so in V also, so that m is less than or equal to n. Also y1 comma y2 comma etc. ym can be extended to be basis for V. Let y1 comma y2 comma etc. ym plus 1 so on yn be a basis for V. Now we shall prove that the set C equal to ym plus 1 plus w, ym plus 2 plus w, ym plus 3 plus w, so on yn plus w is basis for V by w. Let x plus w belongs to V by w, then x equal to a1 comma a1 y1 plus a2 y2 plus a3 y3, so on an yn, and hence w plus x equal to x suffix m plus 1 plus x m plus 2 plus so on an plus an yn. Therefore, C spans V by w to prove that C is linearly independent in V by w. What is V by w? V by w I will say quotient space. Let B m plus 1 comma B n belongs to F. F is a field. So that B 1 y m plus 1 plus w, B 2 y m plus 2 plus w, so on plus B n y n plus w equal to 0, and hence y m plus 1 plus so on plus B n y n for some B 1 comma B 2 comma etcetera B n B m belongs to F, or equivalently minus B 1 y 1 plus minus B 2 y 2 plus so on plus minus B m y m. Since y 1 comma y 2 comma etcetera y n is a basis for V, we get that all b's are zeros, and in particular B m plus 1 equal to 0, so on that equal to B n, that means B n is also 0. Thus, C is basis for V by w. V by w is a quotient space, and hence V by w and w are finitely generated, and dimension f V by w equal to n minus m, that equal to dimension f V minus dimension f w, or dimension f equal to dimension f w plus dimension f V by w. Remark, the converse of above theorem is also true, that is w and V by w are both finitely generated. This completes the proof of theorem. Next one. If W be subspace of vector space V over the field F such that both W and V by W are both finitely generated, prove that V is also finitely generated and dimension V equal to dimension F W plus dimension F V by W. Proof. Let dimension F W equal to m and dimension F V by W equal to n. Let x 1 comma x 2 comma x m and y 1 plus w, y 2 plus w, y 3 plus w, so on y n plus w be basis for w and V by w respectively. We shall prove that B equal to x 1 comma x 2 comma etcetera x m, next y 1 comma y 2 comma etcetera y n is a basis for V. We have to prove that L of B equal to V and that B is linearly independent. Let x belongs to V, then x plus w belongs to V by w, and hence we can write x plus w equal to a 1 y 1 plus w plus a 2 y 2 plus w, so on a n y n plus w for some a 1 comma a 2 etcetera a n belongs to F. Part 2 implies that x plus w equal to a 1 y 1 plus so on a n y n plus w, and hence x minus a 1 y 1 plus so on a n y n belongs to w. So that x minus a 1 y 1 plus so on a n y n, that equal to b 1 x 1 plus b 2 x 2 etcetera b m x m. Therefore, V equal to L of B. To prove that B is linear independent over F. Let B1 comma etc. Bn, A1 comma etc. An belongs to F. F is a field such that B1 x1 plus so on Bm xm plus A1 y1 plus so on An y1 yn equal to 0. That is A1 y1 so on An yn equal to B minus, we are transposing LHS to RHS, minus B1 x1 plus so on minus Bm xm. So, and hence A1 y1 plus w so on plus An yn plus w equal to A1 y1 plus A2 y2 etc. An yn plus w, that equal to w, since y1 plus w so on y1 plus w is a linearly independent in V by w. It follows that A1 equal to A2 equal to so on An equal to 0. Therefore, B1 x1 plus Bm xm equal to 0. Again, since x1 comma x2 etc. xm is linearly independent, we get that B1 equal to B2 equal to etc. Bm equal to 0. Thus, B is linearly independent, and therefore, B is basis for V, and dimension f of V equal to m plus n, that equal to dimension f w plus dimension f V by w is a this completes the proof of theorem. Next theorem, let L be any straight line in the Euclidean plane. Prove that the set of all straight lines parallel to L forms vector space over R whose dimension is 1. Proof, let W be a straight line passing through the origin and parallel to the given line L, then W is subspace of a R square when is treated as vector space over R. Also, dimension R W equal to 1 for any non-element of W, that is a point of W other than origin spans W, then the cosets x plus W for x belongs to R square are precisely straight lines parallel to W or equivalently to L. Thus, W coincides the set of all straight lines parallel to L, and R by W is a vector space over R whose dimension is R minus R, that equal to 2 minus 1 equal to 1, hence proved. Theorem, let Q be the field for rational numbers, then a real number system. R is a vector space over Q. Since Q be a subfield of R, prove that R is not a finitely generated.